Well, it is my pleasure to introduce Dr. Asmeret Berhe. She is currently a professor of soil biogeochemistry and the Falasco Chair in Earth Sciences at the Department of Life and Environmental Science at UC Merced. She got her PhD in biogeochemistry from UC Berkeley. She then moved on to get the University of California President's postdoctoral fellow to do a joint postdoc at UC Berkeley and UC Davis. She's received many awards, including the Fallow and Jones Simpson Medal from AGU, the Fallow and Bromery Award from GSA, NSF's Career Award, and she is an inaugural member of the U.S. National Academies of Science, Engineering, and Medicine's New Voices in Science, Engineering, and Medicine. She generally studies biogeochemical cycling of essential elements in the soil system, especially looking at carbon storage in the soil system. She has a great talk, TED Talk on her website, as well as a comic, and these are some of just a couple of the great science communication devices that she uses. So she's going to talk to us about soil and what it's got to do with climate change. Take it away.
Thank you so much, Brandon, for that nice introduction, and Michael for the invitation, and everyone. As I was telling folks earlier, I have some really fond memories from my time at Salt Lake and the university when I spent 2 weeks there taking the stable isotope course that Jim and Turi are running. So it's really wonderful to be able to talk to you all today. I'll start sharing my screen right now, which should be set. I hope you see it well, right? Okay, so, and I will try to talk about how me as a soil scientist thinks about climate change, right? Which I know is a little different than how geologists, especially solid earth geologists, think about these processes. And so I'll share with you some of the general discussions around why soil has come out to be a prominent, kind of piece of the puzzle to address the climate challenge. But then the rest of the half, I will talk about actually going deeper into the soil profile to understand how much carbon is stored in deep soils, etc. I'll start by telling you a little bit about the kind of work that we do in my lab. So we are a soil biogeochemistry lab, and we try to aspire to be a lab that leads in making positive contributions in the justice, equity, diversity, and inclusion space in the academy in particular, as we train folks and study a range of physical forcings in the environment that affect essential soil processes. In particular, the forcings that we focused on over the years were largely around rather rapid physical change in the environment that occur as a function of erosion that causes lateral redistribution of mass, including topsoil and associated soil organic matter, and fires and the combustion of organic matter in biomass, and then topsoil and the implication for carbon dynamics especially, but also other processes in soil too. And then we've thought quite a bit about the impact of changing global change variables, and particular changing atmospheric temperature and changing amount, distribution, and timing of precipitation, and how they affect the overall cycling of carbon, nitrogen, and phosphorus, in particular, the stabilization of these essential elements, in particular carbon in the soil system. We've spent a lot of time thinking about, in particular, one pool of carbon known as the pyrogenic carbon, which is just a fire-altered pool of carbon that is formed during incomplete combustion of biomass during forest fires and things like that. And how, overall bulk soil carbon, as well as pyrogenic carbon and nitrogen and phosphorus, are affected by these processes in soil, how they are redistributed vertically down the soil profile and laterally in the soil system, including their export from terrestrial and aquatic systems, the role of typically nano-sized natural metal oxides in soil in their stabilization. And from time to time, we also are able to take a much broader view to understand this dynamic two-way relationship between soils and human communities using a political ecology lens. And for those of you who are not aware with this terminology, it basically means using political economic theory frameworks to understand human-environment relations, in particular those having to do with property rights and governance and things like that. And today I'll focus my talk on two major sections, as I mentioned. First, to talk about how a soil scientist like me thinks about soils in the context of climate change, in particular focusing on the storage and persistence of carbon in soil, and then the role of management, in particular management of working lands, and addressing the global soil degradation problem, and how they can help with climate mitigation. And in the latter part, I'll talk projects that we have been working on to understand whole soil carbon dynamics. By that I mean factoring in the entire depth of the soil profile, which to most soil scientists is really, really super deep. As you may or may not know, a lot of what we know about carbon dynamics is actually built on mostly around 10 to 50 centimeter depth of soil. Partly because of how obviously it's not easy to sample deep, but partly also because of some biases we've had to near surface processes. We've got some huge blind spots when it comes to deep soil processes. And in my context, deep means anything that extends all the way to the bottom of the saprolite, so right before bedrock. And so we'll talk a little bit about that in the context of a few studies that we've been working on before I conclude. Okay, so to start with the first part, let's start with some basics, right? We all know that we have a major climate change problem obviously occurring because of this massive amounts of carbon that we keep releasing into the atmosphere from combustion of fossil fuels, as well as land use change. And I think it's important to highlight before we move any further that everything that we've experienced as a, as a function of, or as a result of climate change is only reflective of the half of the problem that we've created for ourselves when it comes to carbon emissions. And it's only reflective of half of this, carbon emissions because the natural ecosystems, including land and oceans, continuously take up this excess carbon that we've been releasing into the atmosphere through additional sequestration that has been happening. And I think I like to talk to folks, especially non-scientists, when we discuss this point that we can almost think about this as the natural ecosystems bailing us for half of the problem that we've created for ourselves. But the question is, how long can they continue to bail us, right? How long can they continue to do this? And for me, I'm interested in thinking about how the soil system operates when it comes to the climate system and climate dynamics in general. And I like to remind folks here again to go back to the basics for a minute, that obviously there's a lot of carbon stored in world soils because of the imbalance between the processes of photosynthesis and decomposition. In particular, because the soil system has been able to stash some of the carbon that comes in through photosynthesis in a soil carbon bank and locking it away there for long periods of time, for hundreds and even thousands of years. And soil is able to do this in particular because the carbon, once enters the soil, a big part of it, at least, a big part of that carbon pool is able to form association with minerals, either directly bind to the surfaces of reactive soil minerals or be associated physically with minerals because it gets encapsulated inside mineral aggregates that make it hard for water, enzymes, and even microbes to get access to that carbon that's protected inside these aggregate spaces. So we're talking about this as the physically protected pool of carbon, and then the carbon that is, in this cartoon attached to the mineral surfaces as being carbon that is chemically forming association with soil minerals. And we can think about this mineral associated carbon in many ways as a saving account in soil. It's different than the carbon that comes in and out of the soil system rather quickly, which is the particulate carbon that results from input of vegetation, for example. But that pool rather cycles pretty fast, and it has to cycle fast to support the life that the soil system is able to maintain, right? So in many ways, to me, it's helpful to think about this by extending that bank analogy, in that the particulate carbon that enters the soil, a lot of it, and then cycles fast, is akin to a checking account that we use to pay our bills, and it allows the soil system to support living things with their food and energy source and nutrients provision too. But then these mineral associated carbon pools, though, are what help build up carbon stocks in soil over, again, millennia and longer. And these processes are also largely responsible for why now the soil system stores twice as much carbon than the atmosphere and vegetation combined. And the significance of this is that because the amount of carbon stored in soil is so large, that a small increase in the amount stored in soil, or the amount that flows from the soil to the atmosphere every year, can have a huge impact for the maintenance of the Earth's climate. So all seems great until this part, until we realize that the soil system that actually is such an important reservoir of carbon in the Earth system is continuously now being degraded by human actions. This is a fairly recent report from about almost 2 years ago now, that shows the global distribution of soil degradation, which basically shows you that virtually no continent is immune. No soil region in the world is immune from degradation. It just varies in how severe the degradation is, basically speaking. And what this means is soil degradation by human actions, in particular because of intensification of agriculture and deforestation and associated human processes, are now not just compromising the ability of the soil system to support the needs of human beings and other living things on land, i.e. our food, feed, fiber needs, but it's also compromising the ability of the soil system to store carbon, right? Degraded soils don't store a lot of carbon. In fact, they lose a lot of carbon as the degradation is happening. And in fact, this was nicely illustrated recently in the latest global carbon budget that was released, to show that land use change in particular is now a major source of carbon that's released to the atmosphere, in particular from deforestation, but also from intensive agricultural production systems. But the report also highlights how there is a significant sink potential for carbon that could exist in soil if we were actually able to rehabilitate all this agricultural land that is degraded and now being intensively cultivated. So in essence, what we're talking about is that soils can either be part of the solution or the problem when it comes to climate change, and in particular, how we manage working lands can be an important part of that equation. A fairly recent study by Jan Sandeman and others showed that in the last 200 or so years, we've lost 120 billion metric tons of carbon from the top 2 meters of soil alone, just simply by how we've been using soils and agricultural systems. And so there's a whole lot of loss happening. But what we also know is that if we can mitigate soils, we can address at least a decent part of the climate crisis. This is also a fairly recent paper that was published by a team of geoscientists that kind of nicely illustrates where we are right at this point in time in terms of atmospheric carbon dioxide concentration, and it compares it to different geologic periods and past climates in those geologic periods. And then it's able to superimpose what we know right now about potential future pathways for the Earth's carbon, the Earth's atmosphere's carbon accumulation. The story here is that if we continue in business as usual model and continue to release large amounts of CO2 into the atmosphere, we're going to end up at this pretty high carbon concentration scenario. But if we actually reduce emissions, which is what we have to do, which is a non-negotiable before we get to any of the other issues, then we can actually avoid the catastrophes that could be associated with really extreme scenarios. But if we actually were able to reduce emissions plus managed our soils effectively in a climate smart manner and actually use these soils to pull CO2 out of the atmosphere, then we actually have a real potential to bend the curve and pull the atmospheric CO2 concentration below even potentially the extreme scenarios that we're expecting. And in fact, a lot of studies at this point agree that mitigation and adaptation to climate change is going to require adaptation of diverse solutions that first and foremost include reducing emissions of CO2 from fossil fuel burning, but then also will require these climate smart management practices. And that if we want to limit warming to 1.5 degrees C, we're going to just have to, it's a must that we reduce emissions and also practice these negative emission practices that allow us to pull carbon from the atmosphere. And, you know, kind of the good part of the story is that we know what to do in terms of how we need to manage soils in a climate smart manner. There's really no surprises there. We've known for a long time and how we can manage soils in a sustainable manner. This figure, I really like it because it helps demonstrate the average greenhouse gas reduction potential that can be derived from a variety of different options on the x-axis. And then on the y-axis is the area where we can actually practice these options, realistically speaking, globally. For example, there's a huge potential in terms of the average greenhouse gas reduction that we can derive from restoration of histosols, organic soils. So something like wetland soils, soils and mangroves that we were talking about before the seminar starts, and things like that. But realistically speaking, the climate envelope that actually allows for wetlands and mangroves to exist, the geographic limit is so much so that you know, there's very little area globally where this can be practiced. So in essence, we're down to about anywhere up to 1.3 petagrams of CO2 equivalent that we could pull from the atmosphere per year by restoring histosols globally. But there are a whole host of practices that we can practice in very, very large areas around the world, including managing our croplands to reduce carbon emissions to the atmosphere, and in fact make them able to sequester carbon by reducing tillage, by reducing the amount of agricultural chemicals we add to soil, and even adding things like compost and other things that help with carbon storage in soil, by managing how we use pastures and grazing lands, in particular avoiding overgrazing and the associated degradation of soil, and even by choosing enhanced varieties of plants that have deep roots, as we're going to talk about later, or even applying carbon in the form of a whole host of things, including biochar. But so we're talking about here charring excess biomass and returning that to soil as a way of increasing the water and nutrient holding capacity and potential plant productivity in agricultural soils, which are things we could practice across a whole vast number of areas around the world, right? All of these things then, even though their greenhouse gas reduction potential is not super high, like restoring histosols or managing rice paddies better, but they could still have huge potential because of the large scale area that we could apply them. And of course, there are these middle of the road options such as managing water systems and others that actually give us these benefits. In fact, there's a global effort underway right now that started in France called the 4 per mil effort, which is trying to encourage land managers and governments around the world to work towards improving the carbon stored in soil annually by 0.04%. The idea here is that if we can actually manage to do that, fully reach the potential of increasing carbon stored in soil by 4 per mil globally, then that's equivalent to, you know, offsetting carbon emissions into the atmosphere from 1/3 of all CO2, of all fossil fuel derived emissions of CO2, i.e. it could take out about 3 gigatons of carbon from the atmosphere. But I don't want us to get caught up in the idea of how effective is it or how likely is it that we can achieve 100% of the potential of this 4 mil effort, right? It doesn't, in many ways, the end goal doesn't necessarily need to be 100% for this to make a huge difference, right? We just need to start heading in the right direction from where we are right now towards sequestering more carbon in soil to actually see a potential for improving soil conditions as well as in reducing the atmospheric burden of CO2. Grissom, in a paper that was published also a couple of years ago, did a really nice job of documenting where is the carbon mitigation potential as far as different ecosystems and management systems are concerned. And obviously clearly shows that managing forests, in particular reforestation and avoiding forest conversions, is where there's a huge potential to be gained by the global community. But obviously, you know, as we saw in that figure, in that previous figure, by the way, these numbers largely agree between the two studies, then you can have quite significant mitigation potential that could occur by 2030. What I really nice about this is also that he also, and they, I should say they, also nicely illustrate how, you know, which part of this option is cost effective or versus things that are more cost ambitious, right? Things that have to cost money. And obviously, as you can realize that, there are things like trees, adding trees into croplands, or even adding biochar, or even reducing reforestation. Those all have costs associated with them, right? A significant cost associated with them. But relatively speaking, avoided forest conversions or even nutrient management in agricultural soils, where we're reducing the use of synthetic agricultural chemicals, or even avoiding draining of peats or preventing those ecosystems from being drained in the first place, or putting in legumes, nitrogen-fixing species in agricultural fields, in grazing lands in particular. All of those are, relatively speaking, pretty low-cost options. And generally speaking, we can actually achieve 1/3 of the climate mitigation potential that we need in a pretty cost-effective manner if we only adopt natural climate change solutions. And all of them, as you can see here, also come with multiple co-benefits associated with improving air quality, biodiversity, water quality, and water provision overall, as well as soil health. Pete Smith and others go a step further and actually link soil carbon sequestration with the United Nations Sustainable Development Goals. The idea here is that if the world, as the United Nations has outlined, would like to address issues, major issues of poverty and hunger and all sorts of, you know, kind of existential issues that humanity is facing globally, we can actually do quite well if we think about improving soil health first and foremost, because that's really where we're deriving a lot of our resources, and that's where people are making their livelihood from land. And they do really nicely. We don't really have a time to go through these options, but what they really do is they nicely illustrate how soil carbon sequestration underlies a lot of the solutions that are proposed for major global issues that we have identified as a global community as key development goals we would like to achieve to ensure you know, fair and sustainable livelihood for all human beings on the face of the earth by 2030. There's some ambitious goals here, obviously here, but if feeding the human population is a priority, if maintenance of ecosystem health is a priority, then the argument here is we cannot do without addressing the soil degradation issue globally. And doing so also has so many other benefits, including maintenance of the Earth's climate, because adding more carbon to soil and keeping that carbon to soil obviously means reducing the atmospheric CO2 burden. So I hope in this first part, I've convinced you that soil is an important regulator of the Earth's climate, has been historically a victim of climate change and human actions, but it also offers multiple powerful and cost-effective solutions for climate change mitigation. Okay, I'm going to switch gears a little bit now and talk about deep soil organic matter dynamics. And I realize that some of you geologists might laugh by what I consider deep. But this is pretty deep for soil scientists, trust me, right? Um, um, but I want to start with some real considerations though, right? As I mentioned, a lot of the data and information and knowledge that we have on soil carbon dynamics is actually biased towards topsoil. And for some, there is a good reason why, right? The highest concentration of carbon is in topsoil. Most biological activity by plants and microbes also happens near the top of the soil profile. So as you can imagine, then this has caused a huge bias in terms of what exactly we choose to study when we want to understand soil carbon dynamics or soil biological processes in general. But as I said, that has meant now we have some major blind spots when it comes to deep soil carbon dynamics, which obviously, if you're looking only at the top, we're missing a whole soil profile perspective. But I'll be the first one to tell you that we also don't quite agree what exactly is deep soil. Part of this disagreement is also part of, nature of how soils develop, right? So here are 4 soils in the US classification system. They're organized from the youngest soil here, the entosoil, that have seen relatively little soil weathering, all the way to altosoil, which is the second to last in terms of how intensely weathered the soil is. So what you're likely to see, obviously, is that if we're talking about carbon dynamics in topsoil, we all, in most cases, basically here, we're hitting the consistent layers. But if we start talking about deep soil, then we have to bring in some additional information about what exactly do we mean by deep soil, right? The depth of this soil, the entosoil in this case, is pretty shallow, and you'd be hard pressed to find an entosoil unless it's, kind of a depositional plane or something that would be deeper than a few tens of centimeters depth, right? So the contact between the weathered soil layers and the parent material is pretty shallow. Obviously, that gets deeper over time until, the altosoil, the whole thing is, weathered soil layer. So there's a lot of discussion, and part of the convention, and I think, I think that makes sense, is that we now refer to everything that's above 30 centimeters or in the A horizon as the topsoil, and everything below the A horizon or 30 centimeters as the subsoil or deep soil. And I keep using A horizon or 30 centimeters mainly because not everybody goes out when they're sampling and actually characterizes their horizons. So a lot of the soil carbon data, and even just any soil data that exists out there, actually doesn't have accompanying horizon designations with it. And as a result, we have to resort either to estimating the depth of the horizon and the boundaries between A and B or AC horizon based on some regional soil surveys, or just assume a number that makes sense. In this case, 30 centimeters, generally speaking, makes sense. 30 centimeters is also generally the depth that is intensely affected by intense tilling, or is the equivalent to the plow layer in cultural systems. So it allows us to at least have some standardization over depth layers. So in systems that vary in terms of the state factors of soil formation, climate, organisms, relief, parent material, and time, then we can try to go out and estimate what proportion of carbon is in topsoil or deep soil, or consider A, B, and C horizons in our carbon accounting, which we almost never do. There's literally, from my grad students' dissertation project, when we were looking, there's literally maybe about a dozen or so studies that have actually tried to estimate carbon stock in C horizons or saprolite out there. Some of you might have quickly said now, right, imagined at least in your head that this is quite an oversight that happens when when soil scientists and geoscientists don't quite work together all the time, right? Because these are layers that you all are very, frequently characterizing. Okay. So the next question that I assume you all have is, how is carbon make it into deep layers, in particular, very deep in the B horizon and C horizon? There are many mechanisms. First of all, we know that plant roots can grow deep. And in the Sierra Nevada, where I work, for example, there are plant roots that are routinely found at about 5-6 meters below the soil surface. And in fact, plants such as grasses are pretty renowned in terms of their ability to stash a big portion of their photosynthetic productivity below ground to allow them to create extensive root networks and also continuously pump carbon into the soil from exudates that they release through their roots. We also know that burrowing mammals of different sorts and even plant roots can mix the soil. So this biological mixing can take carbon that would have been enriched in the top part of the soil profile and stash it deeper into the soil. We also know that quite a lot of carbon across all sorts of ecosystems moves vertically down the soil profile with water. So it's dissolved and moves with water, or there's a vertical mobilization of colloidal carbon that also happens quite readily. We know frost churning or cryotubation in our Arctic systems also regularly brings carbon-rich topsoil, a horizon in this case, and stashes it quite deep in the soil layers. And of course, all sorts of transport processes that have to do with volcanic activity or wind and water erosion processes routinely move topsoil around or material around from one place to another, forming rather deep soils that we know can sometimes have a lot of carbon associated with deep soil layers. Okay, so what we know at this point is that deep carbon storage in soils can account for more than 50% of the soil carbon stock. And from everything we've seen so far, it seems that this deep carbon is mostly derived from below ground carbon input, i.e. roots in particular, and also is a lot more stable and has mean residence time greater than 1,000 years or so when we apply radiocarbon to determine how fast carbon is cycling at different parts of the soil profile. So this is all great, right? There's a lot of carbon in deep soil layers, and we know that it's old and is cycling rather slow. But cycling slow doesn't mean that it's actually inert or not reacting with what's going on near the atmosphere. We've had a few studies recently that have shown that when there is a particular change in environmental conditions, in particular flow of water down the soil system, for example, with changing precipitation type or conditions, there could be a way where deep soil organic carbon can become sensitive to these changes in climate. And under some conditions, then it could be the decomposition of deep soil carbon be responsible for up to 60% of the surface CO2 flux, at least during some parts of the year. So we've had all of these, one study here, one study there, that was able to infer not just these large stock of carbon, but also its potential climate sensitivity. So we were able to take advantage of this location of the Sierra Observatory on the western slope of the Sierra Nevada to observe, first of all, how is carbon distributed in deep soil layers, by basically characterizing the entire soil profile in this case. So A, B, C, and even the CR layer, which is the weathered bedrock that sits right above the unaltered parent rock. So we were able to use geoprobes with the group of geochemists that were part of this study and get cores of soils representing the entire profile, multiple elevation points. These are the 4 major sampling points in the Southern Sierra CZO. And what you basically see when you go up in elevation in the Sierra is that, obviously it starts to get colder with elevation. And the mid-elevation zone in particular, where you have these mixed conifer and the pine oak forests, is characterized by having deeper soils that also have high plant productivity, which basically is partly responsible, the climate and the plant productivity being partly responsible for why there are deep soils there. And previously we had known that the depth of the A and B horizons is deeper in the Swaproot and Providence, these 2 middle sites. But what we didn't know was how deep that weathered bedrock underneath the A, B, and C layers was. And this study was first able to allow us to characterize it. Indeed, in those kind of sweet spots in the mid-elevation zone, not only is the soil deeper, the weathered loose soil, but even the slightly less weathered profile of the soil, the CR, is also considerably deeper and can go all the way to 10 meters in about 2,000 meters above sea level elevation. And this is work that both my grad students, Kimber and Morgan, did as part of their dissertation projects looking at carbon and phosphorus dynamics in this system. We're not talking about phosphorus today, but they were linked studies. Okay, so when we characterize then, this is just a simple accounting of how much carbon is in the soil. And for convenience, I've separated the carbon that is in the A, B horizons from the carbon that's in that CR layer, the weathered bedrock. And I'm doing this because, as I mentioned earlier, there's hardly any studies out there that document how much carbon is in the CR layer and in what proportion of the total it accounts. So that's basically what we're doing here. Across these 4 sites in the Climo sequence, you could see that the proportion of carbon in this weathered bedrock layer, the subrock, actually increases all the way to about 30% of the total. And what's even more peculiar to me is the amount of carbon in this layer in the around 2,000 elevation is actually more than the total soil carbon that there is in the low elevation sites, and even rivals the amount of total carbon, again, that exists in the highest elevation site. I should mention that the highest elevation site doesn't have much weathered bedrock because climate is quite harsh once you get up to that elevation. So there's not extensive weathering of soil. Okay, and obviously it's a lot of carbon, about 30% of total carbon. Is a lot, and it's also a big proportion of the carbon that is generally accounted for in soil. And what we also were able to learn is that the most important climate predictor for how much carbon is stored in weathered bedrock is actually precipitation, in particular deep water percolation, or the actual amount of carbon that penetrates down the soil profile once you account for mean annual precipitation and take out ET from it, so that you're actually just looking at how much carbon moves through the soil system. And then we did a number of characterizations to think about the composition of the organic matter in these soil profiles. And the kind of interesting story that sticks out for me is that you obviously have a lot of fluctuations that occur in the fairly shallow soil layers, both in terms of carbon to nitrogen ratio, which is a fairly decent tool to tell us about how processed the organic matter is. The idea here being that fresh organic matter that's derived from, say, foliage would have a pretty high carbon to nitrogen ratio of 40, 50, depending on what vegetation it's derived from. But highly decomposed organic matter has CN ratio of about 10, maybe even a little bit less. So a decline with depth is characteristically why we expect, because we expect that carbon in deep soil layers is more processed by decomposition and has lost that CN ratio basically until it reaches fairly consistent numbers close to 10. But what you see here is that's not quite the truth, right? Especially in that deep soil layer, both of the deep layers, I should say, that occur in the mid-elevation zone, carbon CN ratio actually remains fairly consistent, right? In the first 4 meters or so. And even below, as it's fluctuating, it still remains relatively, relatively higher CN ratio compared to most of the profile even in the shallow soils. And this pattern is again repeated when you look at the aromatic to aliphatic ratio of the organic matter functional groups that we derive using Fourier transform IR. And what's interesting to me is you should expect the aromatic aliphatic ratio to increase with depth when you have significant processing of organic matter that occurs with decomposition. And so this profile, the most, kind of the lowest elevation site, in both cases consistently shows that the carbon that's there is highly processed, right? But the carbon that exists in the higher elevation systems overall, though, it's again considerably less processed, and it still contains a decent amount of aliphatics, representing relatively simple carbohydrates and things like that, compared to the aromatic species that we expect to be enriched in highly processed organic matter. So not only is carbon persisting in these deep soil layers and is present, is what this is showing us, but some of it might even, as soon as it enters these deep soil layers, might not experience significant transformation. And that kind of makes sense, right? Because you would not expect significant microbial activity to happen in this really deep soil layers, where there is limitation perhaps for oxygen and definitely limitation for resources for the microbes. So it makes sense that if carbon makes it deep into these soil layers, it just persists there for long term. And boy, does it persist. This is radiocarbon data to show how old the carbon is basically in these different soils. And what you see is that the carbon that's in that deeper layer, in particular in the weathered bedrock, can be all the way up to 20,000 years old. And if you think about carbon age distributions in soil, in particular modern soils, 20,000 is almost something you're not going to hear of, because carbon turns over rather fast, right, in soil, unless it's exposed to these kinds of stabilizing conditions in deep soil. But it accumulates, it's old, and once it gets to these layers, it doesn't seem to experience much alterations. And we hypothesize, and this is purely hypothesis as we have no way of verifying this, but we also hypothesize that these wiggles are probably associated with introduction of fairly new organic matter that comes into these deep layers with water that flows down the system. We say this because we know we can see evidence of water moving through these soils in terms of the mineralogy, for example. We can also see evidence of roots growing deep into these soil layers looking for water. So it seems like it makes sense that if water is moving down through these fractured bedrock systems, that it could take organic matter down with it. And if it encounters, weathered soils in pockets, even in the fractured area, that it could leave behind some of the carbon there. The next thing that we tried to do was trying to extrapolate, okay, so how big of a deal is this globally? Let's assume the system that we're studying in the Sierra Nevada can be a useful guide for estimating carbon distribution in weathered bedrock globally. Humor me now, obviously this is huge, there's huge variability in parent material and conditions globally. But what we try to do is take our best estimate of what we know about potential distribution of these types of deeply weathered saprolite systems globally, based on the distribution of different types of parent materials and the climate in the environments where they exist. And we, there's a lot of error. There's a standard deviation here in these estimates is huge, and I'll be the first one to point to you that these are as crude as they get, first estimates of back of the envelope type calculations. But what this data is showing us is that if, say, there are enough areas that we estimate around the world, something around 52.7 million meters square of land exists with that has saprolite that is as deep as 5 meters. And if we can apply some of the things that we quantified in the Sierras with the climate constraints, obviously, that in our systems to these areas, then this can account for additional 201 petagrams of carbon on average that is stored in the soil system. If we can estimate, if you can use this to estimate, depth patterns that include the zero layer, which includes a lot of organic matter, then that number can even be as high as 321 petagram. And that's all new carbon that hasn't been accounted in the current estimates of soil carbon is what we're talking about. So, just to give you an idea of how significant it is, in a lot of the global carbon accounting budgets that are published, there's about 118 petagrams of carbon that the modelers talk about as the hidden soil carbon, which they know carbon's coming into soil, but not quite sure where exactly it is in the soil system. And what I'm telling you is that there's probably about 200 petagrams of carbon hidden just deep in the soil system that we haven't factored in our accounting yet. So that's significant in its own right. But then we also have a series of projects thinking about stability and climate sensitivity of this pool of carbon. And I want to kind of preface this part with a bit of an introduction, a rather rapid one, just to make sure we're all on the same page. So if one is looking at a typical well-drained soil profile, obviously you would expect the percent carbon to drop in an exponential fashion, typically with depth, right? But other important differences that you observe is also that the carbon in the top soil layer is actually enriched in particulate matter, so bits and pieces that you can identify, right, that haven't been decomposed extensively yet. And this carbon in the topsoil also would have high carbon to nitrogen ratio, would be enriched in lignin, a plant-derived compound, and it could even have a pretty high concentration of dissolved organic matter. And this is just my cartoonish representation of carbon, elements floating outside the mineral, outside the soil particles, meaning they're not attached or they're not encapsulated. So these are the free particulate organic matter that could rather rapidly decompose. But if you go deep into the soil profile, you're likely to see most of that carbon be in those mineral associations that I spoke of earlier. It's either inside aggregate spaces, meaning its decomposition is constrained by access to microbes that could do it, or the carbon is again bound to mineral surfaces with chemical bonds, similarly limiting access to microbes that could have decomposed that carbon. And there's relatively less water extractable organic matter. And this carbon is also expected to be older, as you've seen with radiocarbon, and is enriched in microbial sugars and lipids. So, digging deeper into what's happening down the soil profile then is critical, for how we can then interpret what's the dynamics or sensitivity or even transport potential. Because what's likely to happen if you have lateral transport, for example, is if you have surface or near surface transport of water, it's likely gonna take away with it and erode or export only this pool of carbon rich soil. But if you have more intense rain events, for example, that are able to scour stream beds or even cause formation of gullies that can erode deeper soil layers, you can have this more complex and stabilized pool of carbon that is rendered vulnerable to transport and potentially change decomposition to kinetics afterwards. And what we did in this project that was conducted at UC Davis is we exposed the soils to moisture, basically. We irrigated it is all we did, right? But we irrigated a field that had sensors buried all the way down to 90 centimeters because we wanted to measure how the CO2 concentration in soil and fluxes and vary as a function of what, how much water was there and the temperature sensitivity and things like that. So this is basically our way of doing a temperature sensitivity experiment right in the field, but in the process also be able to distinguish between temperature sensitivity during wetting versus drying of soils, or if soils just stayed under ambient conditions. And what we quickly noticed is that obviously, soil CO2 concentration across the soil profile was more sensitive to change in soil moisture during the drying than wetting phases. In particular, this was prominent in the top 30 centimeters soil, but the soil CO2 concentration in the profile during wetting, and more sensitivity in terms of the negative sensitivity in this case, we observed during wetting, right? So what we're saying is that, especially when soils are drying, deep soil CO2 becomes more sensitive to change in temperature. There's a lot more that's released instead of a lot more carbon, so more positive change occurring in this case. And we were able to verify with other measurements and studies that were done in the soils that this change in CO2, that the driving variable here is the change in CO2 production. Not just the change in, for example, movement of CO2 from one pocket to another in the soil. So clearly, under some environmental conditions, wetting caused even deeper soil organic matter that would otherwise have been stable or stabilized to be more temperature sensitive and caused its release, caused it to release large amounts of CO2 more than it would have released without those experimental manipulations. Okay, which I think opened up a lot more questions than answered for us, because I think this is an important aspect to think about. And this also shows up not just the temperature sensitivity, but the overall dynamics of deep soil organic matter ends up becoming important when we think about management practices, because this study, for example, is a study that we're doing in collaboration with folks at the Lawrence Livermore National Lab. And in this study, we were able to sample soils from across many experimental study systems in the US that had paired shallow-rooted and deep-rooted plants in agricultural fields. In this case, the shallow-rooted plants are annuals that they cultivate. They vary from site to another, but all the deep-rooted perennials are switchgrass plants that are also used as part of biofuel production systems. And what we clearly see is planting soils with deep-rooted perennials such as switchgrass clearly introduces a lot of carbon into soil. And we are also able to use radiocarbon to show that this additional carbon storage is actually coming with the input of new carbon from the switchgrass. And the new carbon input extends all the way down to 3 meters below the soil surface. So hugely important. And there's been some estimates, for example, how significant deep soil carbon dynamics can be as an overall contributor to natural climate change solutions. And the numbers that are usually thrown around is that enhancing root phenotypes or using a better variety of crops that have more extensive, deeper rooting systems can actually have a global potential for CO2 mitigation that could be up to 1 petagrams of CO2 equivalents per year. And keep in mind that putting deep-rooted perennials in soil and replacing some of the shallow-rooted annuals that we're used to using in cultivated systems also has a huge potential for restoring soil health overall, nutrient dynamics, and even maintain structural stability of soil. So with that, I'll just conclude that there's a lot of carbon, more than half of that carbon in soils typically can be found in deep soil layers. And so much is stashed in these layers that are hidden from a lot of characterizations that we do in the soil community, in particular in weathered bedrock. And we've also started seeing data that deep soil carbon can be active or at least activated under the right environmental conditions. And this is not even touching upon the climate sensitivity of deep soil carbon in permafrost systems that could be rendered even more sensitive to change in climate if they were thawed and drained. And with that, I will just say that I hope you all agree after listening to the talk that soils could be an important part of the solution for climate change and even offer powerful and cost-effective solutions. And that if we're really going to understand the true potential of soils to contribute to climate mitigation, I think it becomes important for all of us to dig deeper and figure out not just the mechanisms by which soil is able to hold on to a lot of carbon, but also where in the soil a lot of this carbon is held. A lot of this work would not have been possible without some awesome collaborators that we've been working with for many years, and funding sources, in particular, the US Department of Energy and the National Science Foundation. Thank you all.